First, allow me to introduce myself. I am Samia Kirakara, teacher and researcher at the University of Vijaya and a member of the LMO lab. Today, I present one of the studies conducted in our lab, which focuses on sustainable packaging. The title is Barrier Properties of PLA K2SAN, FE mouth clay nanocomposites for sustainable packaging applications. Before introducing our objective, please before introducing our objectives, let's take a few seconds to recall the problem. We are addressing the extensive use of petroleum used based in Algeria. So it is known that most packaging in Algeria is still made from the petroleum-based plastics, polyethylene, polypropylene, and polyethylene terephthalate for both water and so on. Also, Algeria imports about 1 million tons of plastic raw material each year, so we depend on these plastics. And the worst point is that about 500,000 tons each year are not collected or are mismanaged. So the objective of this study, my team and I dedicated to advancing sustainable packaging solutions. Currently, we are focused on developing PLA K2SAN, iron mold, clay, nanocomposites to enhance their barrier properties for food packaging applications. And the presented study today serves as preliminary investigation designed to explore the functionalities of these nanocomposites, specifically their structure and barrier properties. So let's go through the biodegradation. It is just a reminder. So this image illustrates, as is known, the difference between degradation and biodegradation. So it is known that degradation refers to physical or chemical breakdown of plastics into small fragments. So often, of course, due to sunlight, heat, and mechanical stress. The slide before, the biodegradation, please. Before, yeah, this one. So I'm talking about the microplastics based fragments from the degradation. And it's now known for everyone that microplastics or nanoplastics are everywhere, even in our body, brain, and cells. So the biodegradation is our second, and I think the only option, because it is a biobiological process where microorganisms such as bacteria, of course, break down these fragments into natural substances. So in this study, you can go through the next slide, please. In this study, our matrix is the PLA, and the K2SAN is used just as antimicrobial agents. Nanofillers used in this study are AMAWF-based Arum BDC and clay C30B. And this diagram helps explain how the combination between these two fillers improves the barrier properties of the PLA K2SAN matrix. Now, in the case of the AMAWF alone-only system, molecules can diffuse through the porous AMAWF particles. And if you take the clay as only system 2, diffusion is forced to go around the impermeable clay layers, increasing the path length slightly. But if you take the combination, both of them, both effects occur also. So diffusion must travel around the clay layers and interact with the mouth structure, creating tortuous and complex pathway that strongly reduce permeability and migration. This synergistic mechanism explains the enhanced barrier properties observed in our system, as we will see in our results. So let's explain the most barrier properties introduced in this study. So the first is permeability, absorption, migration, and sorption. Let's begin with the permeability, please. So our test performed using the CAP method according to ISO 7783 that measures mass change over time under controlled conditions like temperature and the humidity, and this test is known. The second one, absorption. The test followed STM D57098 to assess the water absorption of biopolymer samples, and this one also is very known. And the third one, migration. The tests followed EM 1186 total immersion method to evaluate the total substance migration from PLA, K2SAN, and composite fields. Two food simultans were used. The first one is 50% ethanol, and the second one is 3% acid acetic. And the last one is sorption, where water vapor sorption was measured at 50% relative humidity and 23 degrees Celsius using climate chamber. The test is explained in this slide. Then let's go to see the experimental part of this study. The next slide, please. Great. So the next slide, please. So here we will talk about the synthesis of our MOF-based iron, BDC. Three main steps actually are followed. The first one, preparation of the first solution. So it is about dissolving terephthalic acid in DMF. The previous one, please. Yeah, I'm explaining the synthesis of FeBDC. So under stirring for 15 minutes. And the second solution, here our iron dissolved in water, then the cluster added were dissolved in distilled water and stirred for 50 minutes. The final mixture and recovery, the two solutions were combined and stirred overnight so after 24 hours, the resulting precipitate was filtered under vacuum, washed with DMF, and dried at 100 degrees Celsius overnight. The ground into fine powder. This is about the synthesis of MOF. Synthesis of the composites, MOF, and clay. This protocol ensures good dispersion and possible physical-chemical interaction between the two fillers, even without coupling agents. So first, we disperse the clay in water and ethanol mixture, stirred and sonicated below 25 degrees Celsius. Also, the MOF dispersed similarly and the same temperature and same conditions. Then the both solutions were added to each other, and the mixture was centrifugated to remove solvents, then dried it at 50 degrees Celsius for 12 hours and obtain our composite powder. Next, please. So here the formulations were prepared using twin screw micro extruder designed for small scale melt processing. And for all materials used here, PLA as matrix and Ketozan as agents of as antimicrobial agents were dried at 60 degrees Celsius for 24 hours before processing. And for each formulation, about 12 grams of PLA, pure or blended with fillers, were loaded into the preheated chamber at 180 degrees Celsius. Two series of experiments were performed. The first one, PLA 2% Ketozan with a MOF only in different loading, 0.5, 1, and 1.5. And the second series were PLA 2% Ketozan 2, and in this time with different contents of our composites, 1, 2, and 3% with 1:1 ratio. It's worth noting that the Ketozan used in this study, prior to use it, it was washed with distilled water, dried it at 55 degrees Celsius for 24 hours, and subsequently ground and sieved through 200 micrometer mesh to obtain uniform particle size suitable for composite preparation. Next, please. Then the extruded materials, PLA and all nanocomposites, were cut into uniform granules and dried to remove residual moisture. These granules were then placed to Teflon-lined molds between metal plates and pressed using hydraulic press at 180 degrees Celsius. Let's now move to results and discussions. So here we have the FE-MOF tear spectrum to see if our synthesis was successful or not. So here we can see some important bonds. The first one at MEL 564 corresponds to the asymmetric searching vibration of carboxylase group in the ligand, and its shift upon middle coordinations indicates interaction with the middle center. The second one at 1383 band, typical for carboxylase in coordination complex, further confirms the coordination of iron with the ligand. And one another band is very important at 748, likely related to aromatic deformation or FeO bending modes in amount structure. So based on these results, we can say that the synthesis of our MOF was successful. Let's go. Let's continue with the infrared of our composites, MOF and clay. As you can see here, a broad band around 1600 in the clay indicates hydroxyl groups of clay, which shifts in the composites, suggesting interaction between the clay and the MOF via hydrogen bonding or coordination. And bands at 1389 and 1017 confirm the preservation of carboxylase groups in the composites via exchanges in intensity showing interaction with the clay. These results confirm the successful synthesis of our composites because both clay and the MOF preserve their structure. X-ray diffraction pattern of the composite, as can be shown in this figure, the MOF exhibits distinct peaks confirming its crystalline structure. And in the composite, the pattern shows that the characteristic peaks of mauve and broad peak from clay, indicating successful incorporation of the clay in our mauve. So we can say that this indicates successful incorporation of clay on our mauve. Now let's see infrared analysis of our nanocomposites. Just slight shifts of the carbonyl stretching band from 1747 to 1741 was observed in the 2 and 3% composite formulations, and these shifts suggest weak interactions between the PLA matrix and pillars, likely through hydrogen bondings or similar interactions, like van der Waals interactions. TGA analysis. Here, as we can see here, in the DTG curves, we can see that these curves show wider degradation peaks, suggesting altered degradation behavior. And after the incorporation of the mauve into the PLA, the degradation accelerates. We can say that this incorporation accelerates the depolymerization of PLA, but still no significant structural impacts, making the composite suitable for food packaging. Microhardness tests, as this figure shown, the microhardness of PLA-based nanocomposites improves with the iron mauve and iron mauve clay contents. The addition of these fillers enhance rigidity and overall mechanical strength of PLA. The improvement is supported by FTIR analysis, showing hydrogen bonding between the matrix and fillers, which enhances maybe polymer network cohesion and mechanical properties. Contact angle measurements. The change in contact angle of the films at 10 seconds and 30 seconds. And the results for PLA composites modified with 2% chitosan and incorporated fillers too show significant change in surface wettability. The addition of chitosan reduced the contact angle, increasing hydrophilicity, and adding both fillers or the composite further reduces the contact angle, making the surface more hydrophilic. The migration test, as we can see in this table, all films show migration values below 10, meeting the EU regulation, and adding 2% chitosan increases the migration due to the hydrophilic nature and OH and NH2 groups, which favor diffusion. And the addition of clay and the mauve reduces migrations thanks to their barrier effects, creating tortuous diffusion paths that slow molecule passage. These composites balance biodegradability and barrier safety, making them suitable for food packaging application. Water vapor permeability test, as you can see in this table too, while chitosan increases hydrophilicity, mauve and the composite mauve clay improve the barrier properties of the composites by reducing water vapor permeability. So fillers enhance the overall structural integrity of the composite, creating stronger and more denser barrier against water vapor. Water absorption test. This figure presents the 7-day water absorption results of PLA K2OZAN, and their nanocomposites. PLA 2% K2OZAN show the highest absorption, reaching all about 1% or 0. Almost 1 by the second day due to the hydrophilic nature or groups of K2OZAN. Pure PLA reached an intermediate level of 0.7, incorporating MOF and composites progressively reduced absorption to as low as 0.30% after 7 days. This reduction is attributed to the tortuous path formed by the nanoporous fillers, which hinder water diffusion through the polymer matrix. Overall, the results indicate enhanced barrier effects and stable structure over time, confirming the good compatibility and interaction between the polymer and fillers. As conclusion, we can see that this sample study developed PLA-based packaging films reinforced with both MOF and MOF clay composites combined with K2OZAN can enhance barrier properties, mechanical and antimicrobial properties. We didn't put results here, but it really enhances even antimicrobial properties. While maintaining biodegradability, we are right now doing or carrying out some biodegradable testing. Key findings of this study: the composite clay MOF was successfully synthesized and integrated into PLA K2OZAN films. Microhardness improved while minor thermal variation was shown. Also, the composite reduced water vapor permeability and improved hydrophilicity with tortuous diffusion path, which limited water absorption and migration and ensuring food safety. We can say that this PLA K2OZAN composites FE-MOF and clay films show promise as eco-friendly packaging materials, combining durability, moisture control, and biodegradability. And future work, or our work right now, is to confirm actually the antimicrobial activity and toxicity for food safety, and optimizing the MOF and the clay loading. Also, do some testing about real condition, biodegradability, and environmental impact. And thank you so much for your attention.